invited by geoforskning.no to give this speak, and it's sponsored by my future employer, Spring Energy, and the title is Using Rock Physics to Reduce Exploration Risk on the Norwegian Shelf. So I'm pleased to see such a nice big crowd. Before I start, I just want to ask you, how many of you consider yourself as geologists? And geophysicists? And the rest were engineers? Looked like it was 50-50 geologists, geophysicists, maybe also petrophysicists. Okay, so I suggest that you ask, if you have questions, you can interrupt me and ask if something is unclear during the talk, but maybe for the discussion it's better to wait till the end. And I'll start with this sort of teaser to introduce what is really rock physics. And I know most of you have heard about rock physics a lot before, either at SRB when I've been there, or when I've been consulting for you, or at other occasions. I consider rock physics really to be the bridge between geology and geophysics. To the left here is the famous amplitude map of the Glitne field, the turbidite field. You see the feeder channel and the turbidite system, submarine fan of the Glitne. To the right, some of you might recognize that these are outcrops in Einsa, also turbidites. Ragnar Knarud is on that picture, and Erik Ødegaard. So really what we want to achieve in quantitative seismic interpretation is to find out what do these amplitudes mean in terms of the geology. And you can do a lot of things qualitatively by going to the field, looking at geometries, the shapes of the turbidites, and recognize the patterns and do qualitative assessment of these seismic and amplitudes. But rock physics is really to try to go a little bit more quantitative, to establish a link between what we see in the seismic and what we see in the outcrops. Quantitative interpretation of physical rock properties, lithologies, and pore fluids. So in this talk, I'm not going to really go and dig into the rock physics details, but I'm going to focus on a few things that I think are important. An outline of the talk is the following. The rock physics link can also be seen as a rock physics bottleneck. I'll show you later what I mean with that. This second aspect, I think, is an important aspect I'm going to highlight. Seismic fluid sensitivity, how that relates to geological processes. Then I'm going to show some examples from the Norwegian shelf. Not really case studies where I go into the details, but just some brief examples from several fields, which actually highlights this issue of how important it is to relate seismic fluid sensitivity to the local geology. I'm going to just briefly mention the issue of scale. I don't have time to go into details of that. And just give you my thoughts on the future of rock physics, what I think personally will be important. Maybe you disagree, and we can have a discussion about that. Three big challenges in seismic reservoir characterization using rock physics, as I see it. First of all, I think we often encounter the problem that we have more unknown variables than known observables. So to really invert the seismic or predict from the seismic, we have a non-unique problem pretty much always. Second point, which I already alluded to, the fluid sensitivity, and also related to that, stress sensitivity, can vary drastically, not only from one field to another, but also within a given field. And both these two first items, I will demonstrate how important it is to understand the local geology. To better constrain the non-uniqueness, you can make the problem more unique. And you can also better anticipate what you expect in terms of oil and gas responses in a given field. It's really important to understand your container, not only the fluids, before you do the interpretation. And of course, what is valid at microscale is not necessarily valid at the seismic scale. In rock physics, we tend to look a lot at the microscale, the microstructure, the texture of the rock, but then we go to the seismic, which is at much larger scale. Is that really, what are the pitfalls there? And that would be a great topic by itself. I'll just briefly talk about that one. Especially the second one will be the one I will focus on. The rock physics bottleneck. As I said, well, we often talk about many different seismic attributes. We can talk about travel time or the NMO velocities. We can do AVO analysis and estimate VPVS ratio from elastic inversion, the acoustic and elastic impedance or intercept and gradients, acoustic impedance and elastic impedance, anisotropy attributes, and so forth. And we can generate many different seismic attributes. What we really want are the geological properties or the reservoir properties: porosity, saturation, pressure, lithology, stress, temperature, etc. To really go from the reservoir properties, or from the seismic attributes to the reservoir properties, we have to pass through this bottleneck. And at the end of the day, we can only obtain 3, possibly 4 acoustic properties: PV velocity, shear wave velocity, density, and sometimes maybe we can get an estimate of Q. Very often we have reliable estimates of only 1 or 2 attributes. For example, I like to talk about this rock physics template that I will show later, where we make a crossplot of acoustic impedance and VPVS ratio, which is just combinations of the ones I've listed here. Here's just an example from the Barents Sea, which illustrate that there is a challenge with more unknowns than independent measurements. This is a VPVS ratio versus acoustic impedance, and these are well-up data, but for a quite wide range, just from a given well in the Barents Sea. And you see here in the first plot, it's to the upper left, it's colored by burial depth. So you see that increasing burial depth will move to lower VPVS ratios and higher acoustic impedances. Porosity will have more the opposite trend. We have also clay content, which really affects the VPVS ratios, and the saturation effects. It's the color scale to the lower right is the log of the resistivity, showing where you have the trend of increasing hydrocarbon saturation. So you see the many geological things that can vary in different directions. At the end of the day, if we only have 2 measurements, we have a problem to separate which factor is causing which property. So one location in this crossplot can be a function of different combinations of the different properties. So we came up with, when I worked with Hydro, together with Erik Ødegaard, to really make geologically constrained rock physics crossplots, where we actually have local geological models to illustrate where we expect different lithologies to locate. And I'm not sure if is there a pointer here, or do I have one? I think so. Just bring up my pointer. So this, for example, is a shale model showing decreasing porosities from very high porosity shale to low porosity showing normally very high BPVS ratios, compared to a clean brine sand, where you also have high porosities, end member here, decreasing porosity going in this direction. For each porosity here, using rock physics model, we have the Gassman theory to tell us what will happen if you add gas. We know that just a little bit gas can cause a drastic drop in BPVS and drop in P-wave impedance. And then you have 100% gas. So here we just show one example of how we can create a geologically constrained rock physics template that can help us. We do this for a given field. And here is just to indicate different things that can change this different trends. If you have an observed trend in the well, or a property in the well, we can start to play this extrapolation game and say, what happens if shaliness is increasing in one direction, for example, from the well? What if cement increases? What if the fluid saturation changes? So we can use these templates combined with the rock physics model are actually constrained by lithologies and fluids and local geology. And these have shown to be very useful tools to interpret both weather data but also seismic data. But really the seismic fluid sensitivity, which is really the big jump from the water saturated point to the hydrocarbon saturated point. We know that gas often gives a very strong response. Oil tends to give a much lower response, maybe located somewhere in between here. But we also see that with increasing compaction or reducing porosity, we see a much smaller or decreasing fluid sensitivity. And that's related to the container. The container, yes, you have a question?
Yeah, I have a question. I suppose the VPVS ratio is based on laboratory samples. If you used in situ VPVS, would you get significant differences?
Actually, we prefer to look at, when we make these, we are talking about the seismic low frequency range. Mm. So when we look at the lab, we prefer to use the dry measurements. If you saturate the core samples, we tend to get some high frequency effects that we don't see in the seismic. So it's a valid point, but here we normally talk about well-log scale to seismic scale. There can also be dispersion or frequency effects between the well-log scale and the seismic scale. What is really controlling the seismic fluid sensitivity? Well, first of all, we know that in loose sediments, it's really the grain contacts. When grains or sand grains are depositing, the grains are touching each other at the grain contacts. And the pressure sensitivity of a sand or a shale is a function of the contact property. But also the fluid sensitivity will be a function, as I will get back to the stiffness of the rock. So the grain contacts really control also the fluid sensitivity. But also the pore shape and the pore stiffness. And it could be cracks as well as the pores itself. The porosity is of course important. But it turns out, as I will show you later, that it's really the stiffness of the rock and the grain contacts and the pore shape that is more important than the porosity itself. Mineralogy plays a role. The saturation pattern in the scale, versus if it's patchy or uniform. We can have viscoelastic effects that also cause frequency dependent effects. And we can have different, the last point is just relative contrast. We have different Capra properties. I'm not going to go into the details of these. I'm going to show you more an intuitive example, because this is really a lot of rock physics theory behind each of these points. I'm going to show you this one, which is kind of an intuitive way to illustrate fluid sensitivity. I call it the slide press and guess, or compress and guess. What is inside the container? And that's really what we are doing in our business. What is inside the reservoir? Of course, first we need to even predict if there is a reservoir there. But really what we're looking for at the end of the day is whether it's gas, oil, or water. So I illustrate with a balloon and a glass bottle or Coke bottle. And the compressibility of a dry rock can be written as follows. It's a harmonic average of the K dry, the minerals, which is incompressibility of the dry rock, the incompressibility of the mineral, and the pore stiffness, K porosity. What happens if we add some fluid inside this balloon or into this bottle? Well, it turns out that you add the fluid effect here, and this is really approximate the way to illustrate gas man, if you heard about the gas man. And what we see is that what is really controlling fluid sensitivity most is actually if this is K, the incompressibility of the pore is low or high. So if it's a stiff pore, this K fluid, this term, if this K porosity is soft, then this one will have a larger effect. So the difference between this and this, the dry compressibility of the rock and the saturated, will be larger if the pore stiffness is soft. And you can think about this intuitively as pressing on this balloon. If it's air or water inside it, you can easily tell by just squeezing it. And that's really what the seismic wave is doing when it's passing in the subsurface. But the glass bottle to the right, whether it's air or Coke inside it, you wouldn't really be able to tell because you wouldn't be really able to press it a lot. So it's a very stiff pore space, and here's a very soft pore space. And that's really also what is significant for our reservoirs. And we saw this, for example, when we looked at, this was actually when I did my thesis, PhD thesis, I looked at both the Grane and Glittne sands. And what was interesting there was that PV velocity versus porosity showed very different velocities for the clean reservoir sands in the Glittne compared to the clean sands in the Grane sands. And we know that the PV velocity will reflect the stiffness, so it has, without going into the mathematical formulations, it is also directly related to the incompressibility of the rock. It's a pressure wave. So what we are seeing here are actually a big jump in velocities, but it turns out that this is, even though the porosities are overlapping, when we first saw this, how did we really explain a change in almost 20% in the velocities? And the pore fluid inside the Grane sands here were slightly heavier oil than in the Glittne, but that could not explain this jump. And it turned out that we actually had rock physics models to explain this, and we found that we could add a little bit cement at the grain contacts. So you can imagine you almost go from a sort of a loose sand, more a balloon-like scenario, to a more glass bottled scenario, as we go from the soft Glittne sand to the stiff Grane sand. And it didn't take, you don't really affect the porosities very much, but your elastic stiffnesses and your velocities drastically increases. And when we first saw this, I remember we went back to the geologist and asked him, so could it be that this is caused by cement, pore cement? And the first reaction was that forget it. There is no cement in Grane. It's too shallow. But when we saw this, we thought this is, first of all, something has to explain this big difference in velocities. And the fit with our rock physics models that said that this is an unconsolidated sand model, and this is climbing up here, and this is a 2% cement, constant cement model. So we thought that, well, 2%, maybe that's not very much. So we went into the thin section and actually looked. And this is a thin section to the left from the Glittne, and to the right here from Grane. And the porosities are overlapping, and they look at the first glance very similar, but when we looked into cathode luminescent light in scanning electron microscope, we could suddenly reveal that some of these quartz grains are coated with a quartz cement, and that they're actually glued together at the contacts. So we went back to the geologist and showed, well, we actually discovered this cement. But then the reaction was, yes, but it's not very much. It's in significant amounts. And then I realized that the challenge of the cross-disciplinary meaning of what is significant in one discipline, what is insignificant for a geologist can be very significant for a geophysicist. So just a little bit cement, as soon as you go from a loose sediment to a stiff rock, even though it takes only a few percent cement, that's very important elastically. And we've seen that quite a lot, and especially in North Sea, but also other places where we have quartz-rich sands, that at around 70 degrees, 70 to 80 degrees, we have this transition from mechanical compaction. This just shows porosity versus depth for clean sand and shale. And we see that shales and sand have different trends. Shales often start with higher porosity, then there is a crossover at some point. Sands maybe start at 40% porosity and have in general higher porosities, but at some point the sands start to cement, and at the end of very deep burial you can have zero cement or zero porosity. And this transition zone, it happens to be at around where we're looking at a lot of our reservoirs, like the Tertiary in the North Sea are often located at 2 kilometers depth. So you can imagine this cartoon to the right illustrates one of the challenges we have, that we can have a container or a sand body that is just below this transition, which has slightly cemented sand, which will have a completely different fluid sensitivity than the loose sand, even though they are located at almost the same depth. And it turns out that this transition can also be related to what happens as smectite converts to illite at around this temperature, which actually releases quartz as a byproduct. It could be that some of this quartz is the source of the cement, of the sands. But also internally in the sands, there could be things that are happening at the same temperatures. There is a lot of debate among geologists about what is really happening in terms of this transition. Some years ago, we did some work with Hans Martin Helseth when I was at Tidro, and we had a nice paper in EAG in 2004 where we actually coupled rock physics and diagenesis modeling. So what we did, we used this exemplar modeling, which is actually a toolbox or a software code for quartz cementation, where temperature and burial history goes in, and then you can actually predict the cement as a function of burial depth and the porosity evolution with burial. So what we have done here is just to take that information at 3 different depth levels and plug in the cement volume and the porosity into our rock physics model. We have contact theory that can actually predict the velocities as a function of cement and porosity. Again, I'm not going into the detail of the rock physics theory. For those of you who know it, you probably heard about the Borgner contact cement model. But these are the models shown over here, and you can see the movements of the points that are predicted. So this is actually a forward modeling of the cement. And you see that here, actually, from the exemplar, we see that even though it's just a few percent from the first value at about 1,500 meters to 2,000 meters, we're just talking about a couple of percent, you see that you're moving in this direction. And of course, the one further down, you go even higher up. So we have this movement here which is really reflected in the diagenesis. We can go first I want to show this. Of course, you can also use this as a tool, and we showed also in this paper that we can predict the fluid sensitivity at different locations. So the purple line here is a loose sand model with depth, starting at the surface, the acoustic impedance. And then the blue line is when it starts to cement. The gray line is the background shale trend, And then the yellow line, my pointer is quite bad here, but the yellow line here is the gas response. So you see that the fluid sensitivity, which is really the distance from the purple line here, when it's loose sand, then it starts to get cemented, so the yellow lines reflects the cementation effect. Now you see that this arrow is smaller. So you see that the change of fluid sensitivity with the transition from the mechanical compaction domain to the chemical compaction domain. We can go the other way and estimate the cement volume, and we had a paper on from the Alvheim team. This was actually a collaboration with Arild and Lundin, where we looked at the well and actually used cross plots of velocity. In this plot we have shear wave velocity versus porosity, and then we just show the target zone from a well, and we use this rock physics model to quantify the cement volume for the reservoir sands. And again, I'm not going to go into the details of exactly how you do this, but it's really just an interpolation and counting contours to estimate the cement volume. This thin section got a little changed here, but it's actually going to show you that there are some quartz cement happening here. And we use the same model. So in this case, we went the other way around, and we actually estimate the cement volume. And we can plot it as a function of depth. And you see here that, well, it's an overburden and there is no cement, but as you get into Boulder and Heimdall, especially the Heimdall formation here, you see that you go from 0 and gradually increases the cement volume. And at some stage here, at 2,700 meters, you almost reach 10% cement. It was interesting also to compare with the Balderhaug et al. 2000, which actually shows about the same change, that there is no cement happening down to about 2,000 meters, but then you see this envelope here, or this triangle, and up to about the same value. So there was a nice match between these two. And again, this is very important to know, to know your container, know the stiffness of your rock before you predict what's inside the container. You have the balloon effect on one extreme, or the Coca-Cola bottle on the other side. And the Alvheim field turns out to be an interesting case, because some of these turbidite lobes that we see on the Alvheim field, this is the Kameleon and the Knele lobe, turns out that the Kameleon has slightly cement on it, whereas the Knele lobe is loose in the upper part, loose sand. And again, it's because you have this transition shown happening right around that level. So in this work that was actually a PhD student at NTNU that I was co-advising, he's just about to finish, and it's a paper that is just coming out in geophysics right now. And it turns out to be a nice case study where we combined rock physics, burial history, and local geology to constrain seismic inversion, and we also used a Bayesian technique to do this probabilistic. Again, I'm not going to go into the details, just showing you the results, and really what was important here to know exactly where this transition point was from mechanical compaction, where the sand started to cement. And here we're just showing the velocities. Here's the PV velocity, shear wave velocity, and density of the logs for the well in the Kameleon structure. And we're just fitting different curves, or predicting the curves, the depth trends, for water saturated, oil saturated, and gas saturated. The red is gas, green is oil, and blue is water. And you see that this transition is happening here, and it's explaining the data that we see in the Kameleon well. I'm going to illustrate you more as a crossplot. You will see over this interval how the properties change as a function of depth. And it's shown here again as a crossplot of VP-VS ratio versus acoustic impedance. And now you see that the different contours groups sort of together the different classes. The brine sands in blue, the green are the oil sand, and red are the gas sands. And then you have the background shade here. And you see, of course, there are overlaps between the different classes, but you see, first of all, that there is a fluid sensitivity that is largest when you have the softest sand, but there is a cement trend here. And when it's more cemented, higher impedances and lower VPS ratio, the fluid effect is smaller. And these are the prediction results shown in a 3D view. And now you see the results with, if you take into account this step trends and do this classification. So we first have done seismic conversion, and then you use this probabilistic, the Bayesian technique to predict the most likely classes of phases and fluids. And in this case, you see here that red is the gas. In the Kamelun well has mostly gas, but in the Knele well we predict mostly oil, which is actually what we observed. Without taking into account this depth trends, you predict gas all over. So it was nice to see that actually taking into account this transition helped us to discriminate where you have gas and oil in this field. And if you go back to this seismic slide, it's interesting to see that, and this is something that I'm not sure exactly what is happening, but if you look at the overburden, there is a dip. I think that it could be that there has been a neogen uplift in the east, so that these have actually been slightly deeper. So you have sort of, and we're actually taking that into account as a reference depth. So it could be that the burial history of this lobe has experienced slightly higher temperature over time on this lobe. And you see that how sensitive it becomes because you're exactly at the transition zone. So these small changes can actually have a big impact. Again, knowing whether you have the balloon effect or the Coca-Cola effect. Okay, I'm going to show you another example from Troll and from Stadfield and Gullfaks, and compare Gullfaks and Stadfield field. So again, showing these depth trends, mechanical compaction domain and chemical compaction domain. We know that loose sands have large fluid sensitivity. It's like a balloon, you compress it. Gasman theory often works well. Also, the large stress sensitivity. I'm not going into the details of it. We use Hertz-Millin theory applies. When you consolidate or cement the rocks, your fluid sensitivity drops, as we talked about. Gasman still works as long as the pores are connected. Hertz-Millin theory doesn't work for cemented sandstones. We have come up with a new model that actually takes into account the pressure effect when the rocks are cemented. Not going to go into the details of that either, but we're going to show you some of the results. What I want to show is that the tarberts, the upper part of the rest of the Gullfaks are actually quite loose sands. And they're actually located, you could think of it as they're located in the mechanical compaction domain, even though they are a Jurassic phase. The Stadfield, which I'm going to compare with, is having almost the same process, but they're slightly more consolidated and they are slightly cemented. You can think of these are just below this transition zone. Of course, we know that the Jurassic fault blocks have experienced some uplift as well, but it looks like Gullfaks has never been at temperatures which actually set off the cementation effect. And this is two figures from Kenneth Defoe and Martin Landry in 2007. And they compare the 4D AVO signatures between Gullfaks and Stadfield. And here is before water injection and after water injection for the Gullfaks field, where they actually show a drastic increase in amplitude. So this is near, mid, and far. And I actually saw a weakening with far as it increased the pore pressure or decreased the differential pressure. So they're injecting and they are reducing the pressure between the grain contacts. Turns out that they were getting close to what they call the fracture pressure. And I think this has been is an interesting issue because there's been a lot of debate about fracturing up and leakage from the Gullfaks. and also, of course, that's also related to the overburden. But for the rest of the sands, if they are loose and you're getting close to zero effective pressure, means that you're getting a soup. What happens with your BPVS ratio when you get the soup? It goes to infinite. And it actually turns out that the AVO so this is the AVO signature of Gullfaks of the monitor survey compared with the stock field. And you see that there is a very strong, what they call class 4 AVO for the Gullfaks, whereas the stock field showed much less effect. Of course, the pressure change there was about the same, but it was from 15 megapascal to 6, 7. So you were higher up on what they call the stress curve. But I think also one thing are the stress changes is also that the container, the quality of the sands in Stotfield were stiffer. So the stress sensitivity and also the fluid sensitivity is different for the Stotfield as for the Gullfaks. And we actually did some work together and looked at this and used some rock physics model and see if we could predict the pressure sensitivity. And this is the in situ pressure is about here for oil and water in the Gullfaks, and if you increase the pore pressure or decrease the differential pressure, you see your VPVS ratio and they're actually continuing to infinite. But for Stotfield, you can have zero pressure, but you still have almost no effect on the VPVS ratios because the cement is keeping the rock. You're not getting you still have a rigidity of your rock. Whereas in the Gullfaks case, you get a soup. And we can actually see here also that the fluid sensitivity is larger and the stress sensitivity of the Gullfaks compared to the Stotfield. Another example from Troll East is now not the amplitudes but more a time shift. So there was some work we've done with the Nordin Skei and also Stålnes that's been presented at some workshops and will also soon be published. What you see here is the Troll East fault block, and this is a time shift at the gas-water contact. What I want to sort of get your focus on is, if you look at the overburden here, see how it kind of rotates upwards and then it's sort of eroded and cut off. And then you have the gas column, the gas-water contact is here, so you have the gas column is decreasing, but the overburden of, especially if you look at the Cretaceous, is increasing. And remember, when you look at time shifts, like this, you look at the time shift between two surveys, where your pressure and maybe also your saturation changes. So the question is then, if you look at this time shift, is it related to varying pressure and fluid changes? We see that the gas column thickness is thickest on the flank, which is here, which can of course explain why we see these time shift differences. If you have pressure changes, they tend to be larger in the gas zone than in the water zone. So just by looking at that picture, that can explain everything. But we also know that these rocks will have seen different compactions. So our fluid and stress sensitivity is a function of the sand container again. So we should be careful not just to invert this picture into fluid and pressure. We need to understand, even in 4D, when we take difference between base and monitor, sometimes we tend to assume that, well, you take the difference, so the geology is cancelled out. We can forget about the geology in 4D. I'm going to show you now that that's not the case. As with the Gullfaks and Stotfield case I showed before, that we need to understand the quality of the container. Because the response you see there is a function of your rock stiffness. And that can vary locally. And especially when I see this overburden, I think that that quality of your container will vary. And if you take just a sketch here and look at two wells, I'm going to show you one well from the flank and one well down flank. I'm going to show you for the somnifuge formation which is where you have mostly gas in this well, and you have a thin gas leg and a water leg over here. But I'm going to show you the shear modulus, which doesn't have any fluid effect, and I'm going to compare this to two wells, the reservoir zones. And what you see then is the brown data points are the western well, high porosity, soft rock. The eastern one, you see it flies up to much higher shear modulus, shear stiffnesses, which again tells us that the rocks to the east are much stiffer than the rocks to the west, which again is probably related to the burial history that is different. You have differential compaction as you go from the flank to the down flank. And again, your fluid sensitivity, think about it more as the balloon effect and the Coke bottle effect. And if we don't remember that here, we will easily misinterpret our time shifts. And here we actually made a model that take that into account, and we modeled the time shifts, and we got quite a good match between the modeled time shifts at the well locations for several wells and the observed time shifts. Okay, so at the end I'll just show you one example from, since the Barents Sea is going to be more and more important. I've shown you now some examples where we look at the transition from mechanical compaction to chemical compaction. But that's more, it's been very relevant in the North Sea, especially in Tertiary, where you have continuously subsiding basins. Maybe you had some rotation of some of these fault blocks. But in the Barents Sea, as you all know, there has been drastic uplifts, and some blocks can have experienced repeated uplifts. So how do we deal with this mechanical compaction versus cementation effect in this area? And this is just, I'd like to show this. It's an overview plot from Ohm et al. That probably most of you know, showing that you have varying uplifts that are quite extensive, up to 1,500 meters around the Loppa high and maybe to 2,000 meters some places. And this is, of course, an interpolated map that is kind of rough. The four different fault blocks can have, I think, the very detailed picture would show many differences than this kind of interpolated plot, but it gives you some view. I'm just going to show you one example here, and this is was work that we did together with Lundin, and it's going to be presented at EAG together with Arild and Håvard. And this is the Myrsildre well. Again, showing the transition from mechanical compaction to chemical compaction. But in this case, as we go from Torsk to Kolmule here, you see it's really cut off. And it looks like this is not really a transition from mechanical compaction to chemical compaction in a continuously subsiding basin. It looks like here you have a fault block that has been buried deep and cemented, then lifted up, and then eroded, and then buried again, and then you have the Torsk on top. So you actually have an erosion contact in between it. And I think in this case, sort of case study, what I'm going to just show you the results of is actually sands located very close to this upper part within the Kolmule. We also saw that sometimes this change from mechanical compaction to chemical compaction happened within the Kolmule. And you see a drastic change here in the velocities as you go from below and above. But again, this is more really a hiatus in between. And I think in the future we really need to understand even more of the burial history, what has happened in between, to really know what has happened also in the gap that we're not looking at here. And these are just the results, some fluid and facies classification results, showing where you have the fluids to the left and facies to the right, and it's just with the calibration well of Myrsildre in the upper and with the Skalle in the lower part. And you see here that the fluids, yellow is gas, predicting gas, actually both before and after, both pre-drill and post-drill. And but slightly more oil is predicted without having the calibration from the Skalle. I think it's also interesting to look at the facies distribution here, showing that we have the cemented sand in dark green, the cemented shaly sand in this case. We also have cemented clean sand and unconsolidated sand in yellow. And actually we see here that in the latter one, after the scholar well, we predict actually more of this loose sand. So maybe we're looking at the surface here because we're really looking at the AVO attributes. I didn't go into the detail of the classification. What we did, we used these rock physics observations in the well to calibrate the AVO and then do the classification of the AVO. But what we see here is maybe that some of this erosion material, the sands, are loose, but what has not been eroded and the columella is still cemented. And to really understand the quality of the sand before we predict that, will control our fluid sensitivities and the fluid prediction. Okay. Talking about cementation is a microstructure effect. It's a textural effect. But as I said, I was going to briefly mention a scale effect, and I think that's very important. Be aware of scale effects. And this is again the outgrowth from Mainza, showing the turbidite layers, sand layers on top of the shale. And if you look at this, we will see that there are thin clay laminas even in a sand-rich turbidite system. If you took a core here, we'd probably see that there are laminations even at a smaller scale. And if you took a thin section from this core again, you could end up seeing something this in the thin section. Clay laminas together with sand grains. When we know that the seismic wave sees something that is much bigger than this outcrop, of course, why the heck do we bother about what is seen in the thin section? But I think that to really understand the geological processes, that there is a link between the small-scale microstructure and the large-scale effect, especially this core cement. Even though the core cement effect is happening at the grain contact level, it will also reflect itself on the bigger scale. But I think in terms of thin bed effects and heterogeneities, that's another story that needs to be modeled, and that's but that would be a different talk. The future of rock physics, as I see it, as I think, especially when you get into complex basins, whether it's Barents Sea or Gulf of Mexico, where you have also maybe salt tectonics, we really need more integration between geophysics and rock physics and basin modeling. And I showed one example that where we actually used some dots to link rock physics to diagenesis, which can be very useful. I think, as we're going to see now, also rock physics trends will be used more and more to constrain seismic migration and full waveform inversions that are coming now is becoming sort of a hot topic. And I think both as an input but also in the inversion part. Of course, more rock physics integration between different disciplines. I've been talking about seismic, but many of you are also working on EM or gravity. And to have rock physics models that are who actually capture the different geophysical observables is needed even more. There's a lot of work going on that now. Rock physics of source rocks, there's a lot of things going on there. Unconventionals, both they have practical recipes, and there's also a lot of work now, for example, at Stanford or other places, also at NTNU, on computational rock physics to really reveal the different effects, what is important at the core scale and even nanoscale, that will be important also at larger scale. Here is just one rock physics model that I've been working together with Tor Arne Hansen at the University in Bergen, where we're looking at the effect of going from granular rocks to cracked media. And I think that's something that I've been working mostly on Tertiary and Jurassic sands in the North Sea that have very granular character. But if you go to carbonates or even rocks in the Barents Sea that maybe have been much deeper and more well consolidated, we tend to, especially in cases where we have uplift, I think cracks are very important in these tight rocks. And the uplifts tend to crack up things, and I know we have a crack expert here, Martin, so he could probably give separate talk about that. But what I want to show here is that first of all, your stiffness, rock stiffness, is very sensitive to the cracks and the pore shape. What we call the aspect ratio is one way to parameterize cracks. And I can show you one that shows the fluid sensitivity, and this is the incompressibility of the wet rock in black and the dry rock in yellow. And then for different aspect ratios. So when it's 1 here, it's just spherical pores. And then you increase so the aspect ratio is 0.01, you have a lot of cracks. So you move in this direction. Your fluid sensitivity is drastically increasing with the occurrence of cracks. And you see originally you have a decrease in fluid sensitivity for spherical pores. But when you have the cracks, you actually increase your fluid sensitivity with decreasing porosity. So the tightest rock actually can have the largest fluid sensitivity. And again, back to this balloon bottle, we need a third one. You need to have a cracked Coke bottle or a broken Coke bottle. Of course, it would be... so, again, it's related to it's showing that you can have a big scatter in elastic stiffness for different fluids for a given porosity. So really what the seismic see is the pore stiffness, not the porosity. And that's an important thing to remember. And this is just an example, again, something in the work we did. This was actually done in Saudi Arabia, and it will be presented at SCG this fall, of a rock physics template taking into account this crack effect. And we're looking at some tight sands, gas sands. And you see that there is, we first looked at this data, these are weather data. We first saw that these were actually just noisy data. But when we started looking into this, rock physics models using actually the differential effective medium model to capture these cracks, we could actually explain these changes by the cracks. So it's a combination of the large scatter is really the soft pores of the cracks with and without gas. The water sands with cracks are up here, and then they go down to so the VPVS ratio becomes very sensitive to the presence of gas in crack media. Okay, I think it's time to conclude. So rock physics is really both a bridge, but also a bottleneck between geophysics and geology. I think we need even more and better integration with geology to help us constrain the non-uniqueness in quantitative interpretation. I've been sort of focusing, the red thread of my talk, I think, has been to really be aware of the rock type, the quality of your rock, the container, and the associated rock stiffness before we start looking for hydrocarbons using seismic data. And if rocks are well cemented, it can be hard to, especially I think, detect oil from seismic. The oil window seems to be located around the depth where reservoir sands start to be cemented in the North Sea and also the Norwegian Sea. But I think in the Barents Sea, the oil window is, did I write this correctly? The oil window seems to be located around the depth where reservoir sands have been cemented. And in the Barents Sea, the oil window is probably within stiffer rocks than in the North Sea and the Norwegian Sea. And I think that's an interesting thing. If you have fault blocks that have been way down and lifted up, and if they're filled with oil, you have a stiffer background rock than what we're used to look at in the North Sea and the Norwegian Sea. There could still be. We know we have also seen that there have been flat spots even from oil recently in the North Sea. But it's really important, I think, to disentangle what has happened with different areas and regions out there in terms of the period. At the end of the day, remember that seismic is the sound of geology. And let's rock together. This figure is, I think, explains a little bit the challenge. And finally, I want to acknowledge, thanks to geoforskning.no for the invitation. Thanks to Spring Energy for sponsoring this event. And thanks to Statoil and Lundin Norway with license partners for data in various fields on our Norwegian shelves that we've been using both at NTNU as teaching and also in publications. Thanks to everybody who has inspired me, and thanks to everyone who has contributed. So, with no names to mention, I don't forget anyone either. Thank you.